For our last session, and our first speaker will be Koen de Boer from CWI, who is speaking about the continuous hidden network.
Okay. Yes, everything works. Good. Hi. I'm going to talk about the quantum complexity of the continuous hidden subgroup problem. But before I'm going to do that, I always start with a few announcements. First announcement is I don't hear very well, so if you have a question, I would like to ask you if you would articulate a little bit more than you usually would. And it's also possible that I walk to you to be closer to you to hear you better. Please, it's for, that's just to make it work a little bit better. Okay? Great. Did I have another announcement? Oh yes, this is joint work with Leo Ducat and Serge Veer. Okay. Yeah, so maybe many of you know already the hidden subgroup problem without the continuous one. So that is actually sort of a generalization of prime factoring and discrete log in sort of sense. And this is again a generalization of this hidden subgroup problem. Instead of over finite groups, this is over continuous groups. And we mean with that like vector space, R vector spaces. Okay? Okay, let's start with the actual talk. I will give you a small overview of this talk. And I will start with an introduction. I will try to motivate why this particular question is interesting. And I will also try to explain where inspiration came from. That's always very important. The next one is the actual problem statement. So what is the hidden subgroup problem? What is the continuous hidden subgroup problem? And it involves lattices. So that is why there is a lattice picture. Then I will give you a global overview of a quantum algorithm. It will be an intuitive quantum algorithm, as intuitive as possible. I mean, quantum is not really about intuition anyway, but okay. And the next one is I will quickly go over open problems because there's still much to do in this topic, and I would love to see other people work on it as well because it's really a beautiful topic. And I will finish with an error analysis because this quantum algorithm, in using some assumptions, it definitely works. But if you drop those assumptions, you need to put a little bit more effort in it to make it work. Let's start with the introduction. So the main inspiration of this work came from this paper of Eisenträger, Helgren, Kitaev, and so on. This paper gives a quantum algorithm that computes the unit group of number fields. Right. And here is where this successful generalization of the hidden subgroup is constructed, is invented. So they made a successful generalization of the hidden subgroup to the continuous hidden subgroup problem. And they also gave a quantum algorithm that solves it. And they use this as a black box to compute unit groups in number fields. And I would like to stress that unit groups computation on classical computers are believed to be very hard. mean, prime factoring, you can compare it with that. Factoring to primes is also believed to be hard on classical computers, but on quantum computers it's easy. And this has a similar flavor, say. Unit groups are hard on classical computers, but on quantum computers it is easy. Okay. And for the crypto people, because this is actually, I mean, this is a crypto-oriented seminar, so this is used to prove a quantum hardness gap between ideal SVP and SVP. So SVP stands for shortest vector problem, and ideal SVP is finding a shortest vector in a structured lattice, and this is finding a shortest vector in an arbitrary lattice. So apparently, if your lattice is if your lattice is based on an ideal structure, it is easier than if your lattice is not based on an ideal structure. And this was, I mean, a while ago, this was believed to be equally hard. And that is where some crypto systems were based on. But this actually showed that that it is actually not equally hard. I will go over an informal problem statement. So we will go to the formal one as well, but first I want to give you some flavor. Given a nice periodic function, like this, find its period. It seems so easy, but it's remarkably hard if you are only allowed to sample a finite amount of points. Okay. And we can also generalize this to higher dimensions. So here, a more psychedelic example in 2 dimensions. And now, the period is a lattice. So that is an insight. In higher dimensions, the period of a function is encoded by a lattice. So the problem statement becomes, given this function, find this lattice. Yes? Okay, let's go to the formal stuff. Okay. So now f is your function, your periodic function. And we are given black box access to a function f from the real space, real vector space, to a set of states, quantum states. So we already allow this function f to be quantum already. Doesn't need to be, but we allow it to be. And you could think of the state of the set S as the states of an n-qubit register. All states of an n-qubit register. And this function should satisfy the following conditions. The first condition is, of course, periodicity. I mean, this is the bare minimum. I mean, if you want to find a lattice, your function should at least be periodic. The second thing is that f should satisfy some smoothness. F should be a little bit regular. If it hops up and down, we cannot really find periodicity in it. The last condition is the most technical one. It's called separable. And it means that the function shouldn't be too constant. So I've made a picture here for you. This is a separable function, and this is non-separable. So if it is too constant, we cannot extract information out of it. In the most difficult example, the function is just flat. And then it is periodic with respect to any lattice. Right? So it should be a little bit non-constant. Non-constant enough. And it's written here. This is like the formal statement. And I don't want to put too much effort in it. So, given a periodic function, Lipschitz continuous and separable, we want to have an approximate basis of the lattice.
Could you relax the separability constraint if you allow just the algorithm to produce any solution that satisfies the other two constraints? So if the function is completely flat, then any lattice you return should be correct.
Yeah, but the idea is that you have a fixed lattice in mind. Right. So, for example, think about the log unilattice of a number field. So if you can trivially just put, so if you don't care about what lattice you find, of course. But But I want to stress one more thing about this. So this is only needed when you want to sample multiple lattice points, and we will see this later, but if you want your dual lattice to be fully generated, that is what it means. But we will go to that later. Okay, so we want an approximate basis of the lattice. That is the goal. Any questions about the formal problem statement? Good. Okay, so.
Do you know what tau approximation means?
Oh, that's a good point. Okay, so if you have a matrix, a basis that's in a matrix, and you can consider a norm, a matrix norm, like the infinite matrix norm, and you just want a matrix that is tau close in the infinite matrix norm to some basis of this lattice. Cool. Yeah. Thanks. Good question. Contributions. Okay. So what did we do? We simplified the algorithm of Eisentrager et al., and we also refined the analysis. So by simplification of this algorithm, you can do this analysis way easier. So what we did was, instead of starting with a sort of sinusoidal initial distribution, we use a Gaussian distribution to start with. We will see that later. And we came up with a complexity that uses explicit polynomials and has all dependencies of parameters. So maybe you remember the Lipschitz constant that is in the problem statement. Yes, you remember the Lipschitz constant? So if your function has a very high Lipschitz constant, what is the influence of the running time? That's like that is what we did, right? And it looks like this. And I'm not going to talk about this. I have a way simpler, a more simpler version. So if your Lipschitz constant is not too large, the algorithm requires a cubic amount of qubits, a quartic amount of quantum gates, and a linear amount of quantum queries to the oracle F. And M here is the dimension of your hidden lattice. Yes? Great. I will go to the high-level approach of the algorithm. I also wrote it down here, so I will stand before it. We first sample approximate dual lattice points. And we do that using a quantum algorithm that queries F in superposition. Then we assemble many of those dual lattices, and we put them in a sort of approximate basis of the dual lattice. And then we invert this dual basis to get the primal basis. And primal basis means the basis of the original period lattice. And this talk will be mainly about the quantum algorithm. So this is the only quantum step. The other steps are classical. So before I want to do that, I will explain some important thoughts. The first important notion is the dual lattice. The dual lattice is sort of the inverse lattice of your lattice. If you make the primal lattice more sparse, your dual lattice becomes more dense. So it is sort of an inverse notion. And this is the explicit definition. And there's something remarkable about those dual lattice points, because they, you can define the following sine functions. Those are actually exponential with an I here, so like sine functions. And those sine functions form a basis of the lambda periodic functions. So I wrote it down here as a sort of slogan, like the sine waves form a basis of periodic functions. And it's like your Fourier analysis. So explicitly, every nice lambda periodic function can be written as a weighted sum of those sine functions. So those are associated with dual lattice points. This is what we call the Fourier decomposition of F. And those CL stars for L star and lambda star are called the Fourier coefficients of F. So they are always associated with the dual lattice. I had some nice animation, but we will not wait for that. And one more important thought is the convolution theorem. So the way I'm going to explain the convolution theorem wouldn't be too complicated. Suppose this is your function f, then this is actually the spectrum of f. It goes on here and there, and those points here are the dual lattice points. And the size of the arrows are like proportional to the size of the Fourier coefficients. So this is how a Fourier decomposition of f looks like. But suppose now that we multiply f by a Gaussian. This is a notation for the Gaussian. Then the Fourier transform of this function looks like almost the same, but with some small Gaussian noise around the arrows. Then I will go to the global idea right now. So this global idea of the quantum algorithm assumes that we have an infinite amount of qubits. We will drop that assumption soon, but for convenience and for ease of thought, you can just imagine all the qubits. So we create the Gaussian superposition. It looks like this. And we query f in superposition. And then the amplitudes will look like this. Applying the Fourier transform, we know that this is like the product of the Gaussian times your function f. So applying the Fourier transform gives us essentially the Fourier transform of f with some small Gaussian noise. And if you now measure...
Excuse me.
So I didn't quite understand how querying the function also affected the amplitudes.
You don't understand why, what affects the amplitude?
So let's say you have
Mhm.
superposition of points in space
Mhm.
that follows the Gaussian distribution.
Mhm.
When you query the function at the points,
Yeah.
you'll still remain in the Gaussian superposition, except that you have the function value entangled with the point.
Yes.
How
So,
do you go from that to
of
this?
course. So this is like it's purely how do you say it, pictographic. This. So of course we should think about this as this should be like in the complex plane and should have a phase, right? So you have like the Gaussian function like this, whoop, and your function goes like whoa. Understand a little bit what I mean now? No, I'm joking. So I'm joking. Look, this is purely pictographic. So what the function, indeed, this doesn't influences the amplitude in that way, but it still works in that sense, because if essentially we do a measurement somewhere here of the second register, and then it works out like this. Yeah, I didn't want to include that. I want to keep it a little bit intuitive, and that is why I don't want it to spoil too much on like technicalities. But it works like this, but with more words, say. Okay? Oh.
So you think about an oracle that encodes f in the phase and not in the amplitude. And the Lipschitz condition is on the function f or on the sort of the function f in the exponent. So for that, you want Lipschitz for like e to the I times f.
So yes. So indeed. So the yeah. Yes. So that is yeah. So that is what I wanted to show with the weird gestures. But yeah, essentially yes. Yes. Okay. Yeah, so any more questions? Great, so we will drop the infinitude assumption soon, but first we will go to the open questions because, yeah, it's super interesting. Great. So the first thing that is like we would like to know is the complexity of the oracle functions for the unit group and principal ideal problem computations. So in this talk, we assumed f to be an oracle function. We can just query it. But in reality, this function needs to be computed, right? It is a quantum function. So we would like to know what is actually the complexity of that function. And this is there's already ongoing work by Bias and Song in this direction. Okay, the next open questions is are there assumptions on the function f that make the complexity better? So we only assume that f is Lipschitz, but it could be way smoother, and we would like to know if it is a little bit more smoother, would it affect the complexity also in a good sense? Great. The third open question is, suppose you know a sublattice of this hidden sublattice. Not a full rank sublattice, but some sublattice. Would that affect the complexity? Would that help you? This is for the principal ideal problem. We can use it in the principal ideal problems. Okay. And then the next open problem is classically. So this part here has a terrible numerical stability. So if we make an error here, this makes this error way bigger. We would like to know if there's an analysis of this particular part of the algorithm that makes the error not too big. And that could save you a factor m in the complexity. That would be very, very good. I'm not sure about that, but it might be. And this is also one of the most interesting ones. I think so. So you have symmetries often in your lattice. Think about number fields with a Galois group. Then your lattice, your ideal lattice of your unit group, has a Galois symmetry. Can you exploit Galois symmetry to improve the complexity of this algorithm? Any questions about those open questions? Oh, yes?
When you say use the symmetry of the lattice to improve the complexity, do you mean just after recovering one vector, apply complexity to get many, or do you want something even better than
For example, yeah.
At any step.
Yeah, but how would it, for example, impact the numerical error?
Yeah, okay. So you want to improve even the quantum phase using that?
Yes. Indeed. Yes. Good. So let's go back to the global idea. And the main problem is that quantum computers only have finitely many qubits. So what we need to do is we need to discretize it and we need to window it. And also one thing is that this Fourier transform becomes a finite Fourier transform. You cannot do a Fourier transform over the reals. You can only do a finite quantum Fourier transform. So let's do it. Let's just do it without just discretize it. And the first thing looks still quite nice. And after querying F, still looks sort of nice, but I want to show you this without the lines to give you an intuition why it could be hard to see periodicity. So if you get this bunch of points, you don't see immediately periodicity, right? So this gives you an intuition why you need many points. You need many queries. So in the ideal case, it is the Fourier transform restricted to the grid. So this is something that we can analyze. We know what this function is. But in the actual case, we do the finite Fourier transform, and that might deviate from this real Fourier transform because the finite Fourier transform cannot read between the dots, right? Understand? The finite Fourier transform can only see what happens on the dots and not in between. So it loses information, and with the loss of information, it has some noise. And the actual question is this close in the L2 norm? The L2 norm is a general measure. If this is close to that in the L2 norm, it means that the probability of sampling doesn't differ too much. Big questions are, how fine must this grid be? And how is it related with the parameter A? Let's go to, so how did we analyze this? So we went from the grid to the real space. And the grid looks like this. Oh, sorry. The grid looks like this. And the Fourier transform on the grid of the function is this messy thing. And we showed that, we have shown in our work, that this is actually equal to the Fourier transform on the unit cube. So we remove the grid lines here. We have just a continuous Fourier transform, but only on the unit cube. And the next step is going to a Fourier transform over the entire real space. And that is something that we can analyze. Yeah? So this is something that we can compute on a quantum computer. And this is something that we can do mathematical stuff with. Good. And the techniques we used to show that those are close is the Uden-Jackson theorem. The Uden-Jackson theorem says something about optimal trigonometric approximation. And this, the way we show that this is close is a more famous technique, namely the Poisson summation formula.
Embedded cheek bones. Embedded cheek bones.
Yeah, so, spoiler. But okay, and we will also use smoothness and Banach-Cheek bounds, but that was reserved for the latest slide, more late slides. But anyway, any questions about this?
I have a question. How do you choose sigma? So to make sure you're not smooth out your lattice.
How do you make sure you?
Deviation parameter sigma.
Oh yeah, so. You can that's a very valid question. You can always make your lattice more sparse by, if you query f, you can also query f, but we first compute, we make f faster. So instead of querying f, we query f times f and v times your input. So you just first apply some scaling to your x, and then you apply f. And this means that your hidden lattice becomes 1 over v lambda. So you can make your dual lattice sparser just by doing this. And so it doesn't really, so we can keep this in a fixed way and just make the, but it does influence the running time, because if you do this, the Lipschitz constant goes up multiplicatively by v. Yeah. Next. So is this close to that? Yes. Good. But we need Q. Q is the amount of points here, the number of points. We need that to be bigger than m to the power m times your Lipschitz constant. And the log of this number, that is the number of qubits. Can everybody see this? No? Yes? Sort of?
It's on the screen.
Oh, fantastic, yeah. Great. Oh, and now I want to do some Banach-Cheek things. So if we are here, we are not really done, because this looks like that we are done. If we sample something here, then the distribution, the probability that we sample something close to the dual lattice point is expected to be quite big, but we still have to do some work. So this function here, the line, the gray line, satisfies, is exactly this function. Do we all agree on this? This is the Gaussian centered at the dual lattice point. And we just sum over all dual lattice points with some constant. And this constant are how high those hills are, and those are all centers of the Gaussians. Good. And we know from the law of quantum mechanics that if you take the square of this function, then is this the probability of sampling x. And we want to show that the probability of sampling an x close to a dual lattice point lambda 0 star is equal to, almost equal to its Fourier coefficients square. Does it make sense? So if you take the sum of all Fourier coefficients, you get 1. You can actually compute this square by taking 2 sums. You arrive at this sum. And what we do is we split this sum in 2 parts. The first part is where k and L star are equal, and the second part is where they are not equal. And I want to show you that this part is actually very small. Because, so, this is one Gaussian, this is another Gaussian. If you multiply those, you get something very small, because at this point this is really small, and at that point this one is really small. If you multiply this, it's small. Okay. So we can scratch this one out. We get only this one. And if x is close to L0 star, the only Gaussian that matters is the Gaussian with respect to this L0 star. If you have like a Gaussian like this, there's a sum of 2 Gaussians. If you have a point close to this L0 star, then the only Gaussian that really matters is this one. The influence of this Gaussian on the value of this on this point is very marginal. That means that we only need to do, we only keep one part of the sum. We only keep the L0 star part. Okay. Right? And now we put this value here. And we put the Fourier coefficient outside. Look. 1. And now we are going to use Banachik and smoothness. And so smoothness is a technique by Banachik and Misciancio and Regev. They show that this is actually very close to 1. So this is equal to the Fourier coefficient. This was the last part of the analysis. So I will give you some summary. So multidimensional periodic functions have a period lattice. Such functions have Fourier coefficients over the dual lattice points. A quantum computer can sample approximate dual lattice points. And enough dual lattice points gives an approximate basis of the period lattice. Good. Thank you for listening.
Are there any questions?
What was the notion of closeness when you were explaining the last part?
The notion of closeness, when I explained the last part.
X's are considered to be close to the dual lattice point.
Yes. So this is quite hand-wavy, but all those notions are all L2 notions. So it is all in the L2 distance. So you have an amplitude over your space. So
define in terms of tau, the approximation that you're aiming for at the end?
Tau approximation, the tau approximation is something different, because that is the approximation of your lattice point. The approximation here is actually an error. So I want to show here that two distributions are close. Distributions coming from a quantum state are close. And you use that, then you use the L-tune norm. Do I make sense?
Well, if I understand correctly, the idea is that you're sampling dual lattice points.
Yeah.
And for that, you are summing up over probabilities of observing points that are close to that.
Yes.
So then the question is, so there are, the support of the distributions is not the same. You're actually taking some kind of a projection. So it's not quite an L2 distance between probability distributions. And there are two things here. One is, how do you reconstruct your dual lattice points from approximate samples, X, and what do you consider to be close enough to the dual lattice?
Can you repeat the last question?
Sorry. So in your summation, you have X close to L0 star.
Yeah.
What
did exactly?
mathematically?
Okay. Yes. So there's also another parameter involved in the main theorem, say. It's called delta. It stands for distance. And this delta can be made arbitrarily small, but you have to pay for it, of course. And so what does it mean? Well, actually we mean X being in a ball delta close to a dual lattice point. And this delta is like closely related to the spread, the deviation of this Gaussian. Do I make a little bit more sense now? So it is. So yeah, you can make this all mathematically sound, but it will take quite some effort and time. Yeah. So yeah, you can also read the paper. Yes.
How do you decide the radius of the Gaussian function?
What of the function?
The radius?
The radius
Yeah,
of what?
of the Gaussian function.
Yeah, so the radius, Gaussian doesn't really have this deviation.
Yeah.
So so this deviation. So that's like an input. So this depends on the input, right? So we have like a delta here, and this delta is this is input given like how close do you want to be to your lattice point, and that is again related to this tau at the very beginning. So this sigma is, so it is not precisely given here, but it's sort of related with the input, with the tau input. So, yeah.
Any more questions? No, the same.
Thanks.